So here we look at a generative adversarial network as the game or competition between the generator and the discriminator. What we see here is a generator, and the generator is a neural network, typically a convolutional neural network, that takes in a vector of random noise as input. And in this particular example, the generator is tasked with generating images of digits. For example, this could be a training set that consists of the MNIST dataset, where we have images of digits from 0 to 9. Then the output of a generator is an image, and we can also call this image a fake image. Not necessarily because it doesn't look like a digit, but because it's generated by the generator. And the training set, these we consider the real images. For example, we envision the MNIST dataset images of digits from 0 to 9. The discriminator is another neural network, typically a convolutional neural network, that takes as input an image, and then it decides if the image is real or fake. So now the generator and discriminator, they are competing in the following way. The generator would like to generate images to fool the discriminator, such that the discriminator cannot tell the fake images from the real images apart. The discriminator, however, would like to distinguish between the real and the fake images. So the generator would be most happy if the discriminator always classifies the fake images as real. The discriminator would be most happy if all the real images are classified as real and all the fake images are classified as fake. So the reward structure that we would like to set up is the following. For the generator, we would like to give a positive reward if a fake image is classified as real, and a negative reward if a fake image is classified as fake. If the fake image is classified as fake, the generator failed to fool the discriminator. For the discriminator, the reward structure should be as follows. Positive reward should be given for classifying a real image as real and a fake image as fake, and a negative reward for classifying a real image as fake or a fake image as real. Here's a visualization from Goodfellow. This is focused more on the data. So what we have here is an image X that is sampled from the data, and images sampled from the data, these are real images, they will only be fed to the discriminator. So the discriminator is a differentiable function d, and then there will be an output between 0 and 1. And since this image is real, and real is associated with outputting 1, the discriminator tries to have a value near 1 for this real image. Now, on the other side, we look at the path of a fake image. So it starts out as some random vector z being generated. And then this vector of random values is fed into the generator network. Again, this is a differentiable function g, and it will take this input noise and produce an image x that is sampled from the model. That means an image X that is sampled by the generator, and you see here an example of such an image. Doesn't look as great as the real image. Then this image is fed into the discriminator. So the discriminator then, the same discriminator as we discussed on the left, will analyze this image, and then there will be two competing goals here. So the discriminator will try to make this the output near 0, and the generator hopes that the output will be near 1. That means that the generator hopes that the discriminator classifies the output as real, and the discriminator up here actually hopes that it can output fake for the fake image. So it wants to output something near 0. Then this is something that you'll often see in the equations. That means that we have this random vector z that is passed into the generator first to produce an image, and then this image is being looked at the discriminator, and so then you get an output. So this d of g of z is the discriminator output for a fake image that is being generated by the generator. So now we look at some links to game theory, but mainly about one particular optimization that is used in the original Gan paper. So this idea of Minimax is that Minimax is a decision rule for that is used in game theory. So it's a decision rule for minimizing the possible loss for a worst case. And we're not really going to look at Minimax as a decision rule, but we're only going to look at a very narrow aspect of this Minimax and Maximin. That is, we want to look at the impact of the order of minimum and maximum in an optimization. So what we'll see is some equation that has the minimum of a maximum or a maximum of a minimum, and we just want to make sure that we understand what is the impact of this order. So there should be some warning. The warning, I think, is mainly that the game theory looks a lot like mixed strategies, and we are only looking at pure strategies where we'll basically look at an equation like a value function, and the value function has some variables. These are the choices of the players, but the players need to choose the variable values, and it's not exactly the same as choosing mixed strategies in game theory. So if you look at this whole idea of Minimax in game theory review, there might be some minor differences. Alright, so player 1 controls the variables x1 and has a value function v1, and higher is better for player 1. Player 2 controls the variables x2 and has a value function v2, but we're not going to use v2. We'll just assume almost that we have a zero-sum game where there's a strict competition between player 1 and player 2. So again, player 2 controls x2. So now we have this idea, it's kind of Minimax. So we would like to evaluate the following equation. That is, we have a function that is the value function v1, that is the value function of player 1, that has the variables x1 and x2. And so we have a maximum over the variables x1 and then a minimum over the variables x2. But what does that really mean? So this type of Minimax is the largest value player 1 can guarantee when he is told the strategy or the variable choices of player 2. So we can think of this as basically a game where player 2 moves first, and then player 1 can observe the choice of player 2 and then make his decision. So in a game, what is better, going first or going second? So in this type of game, it's much better to go second, because you can look at what variables your opponent chose and then you make your choice. So in this example game, we have the player 1 that wants to maximize, and we have the player 2 that wants to minimize. So that is the same as trying to maximize the negative of this value. So these values in here are the values as seen by player 1, and since we have a zero-sum game, player 2 just looks at the negative values, or you could think of just tries to minimize, whatever. So the choices that the players have are either they choose A, B, or C. So it's a game with 3 choices. Player 2 also has the choices A, B, or C. So ideally for player 1, he could choose A, and player 2 would choose C, and then player 1 gets the maximum overall utility, which would be the 8. However, since this is a competition, we'll look at this minimax value and see what does that tell us. So for every choice of P2, we will mark the best choice of player P1. So the first choice that player P2 can do would be A. Okay, so if player P2 chooses A, then P1's best option will be to choose C. So this would give the highest value for player P1, so it would give this 6 here. If player P2 chooses B, then the best option for player P1 would be the 5 here. And if player P2 chooses C, then the best option for player P1 would be the 8. So this is the inner loop of this equation, that is this inner max, that says for every choice of player P2, let's record the best value, the maximum, for player P1. And now player P2 can look at all these options and can say, I would like to choose what's best for me here. That is, player P2 would like to choose this 5 here. And the rationale is the following. Player P2 has to go first and has to choose first. So player 2 knows that if I'm going to choose A, then player 1 is going to choose C and get the 6. If I choose B, player 1 is going to choose A and get the 5. And if I choose C, player 1 is also choosing A and getting the 8. So what's the best I can do here if I have to go first is I will have to select B, and then player 1 will select A, which will give the 5 here. So for maxi min, we're going to reverse this. We'll have the minimum in the interior loop, and the maximum is kind of outside. So what we're doing here is that for every possible choice of player x1, x2 will think about what can I do to get my best value, that means for every possible choice of x1, I will try to minimize this v1. And then over all these minima, x1 can choose the maximum. So now this would be a temporal order that is reversed. Let's look at this in the example we looked at before. Before, just a side comment that this max-min value has to be smaller or equal to the minimax value. Alright, in this visualization, player P1 has to kind of go through all the options, and for each option, player 2 thinks what's my best choice. So if player P1 picks A, then player P2 looks at this first row and picks the minimum value, so it's going to take the 1. And player P1, if it picks B, player P2 looks at this row again and says, hey, 2 is my best value. And for the choice C for player P1, the best choice of player P2 is going to be B, so he would obtain the 4. Well, now player P1 would say, okay, so what I have here is a choice between 1, 2, and 4, and I want to maximize. So the best I can do here would be to get this 4. So the max-min value would be 4. And that's less than the minimax value that was 5. And again, to note, we're not looking at this game theory with mixed strategies and pure strategies. We'll simply look at an optimization. And when we look at this optimization, then it's similar to game theory without the mixed strategies. So we'll just try to visualize that this, or explain that the order of minimum and maximum matters in the optimization. So this is the original Gan equation, where we have this function, a value function of the discriminator and the generator. So, but what does that mean, a value function of a discriminator and a generator? So I have this alternative formulation here. So it would mean that we want to optimize over the weights of the respective networks. So we want to optimize over the weights of the generator network, and we want to optimize over the weights of the discriminator network. So the alternative formulation that I wrote down here just makes these weights more explicit, but I'm going to discuss the equation looking at the formulation that is written down first. So just to clarify what it means to optimize over the generator or discriminator. Okay, so what we have here is an expectation where x is sampled according to the data distribution, and where we compute the logarithm of d of x. This value function b is seen from the point of view of the discriminator, such that the discriminator here wants to maximize and the generator wants to minimize this equation. So the discriminator would like this d of x to be high, preferably should be 1. So for any x that is sampled according to the data distribution, the discriminator would like d of x to be 1. If this d of x is 1, then the logarithm is 0. So if in the best case this would be 0, and now if the discriminator gives a lower score, let's just say 0.5 or 0.1, then this will be a negative number. And then the discriminator would not be happy. So what happens if we output a 0 for a real image? Well, the problem is that the logarithm of 0 is minus infinity. So what this equation does is it really, really penalizes small numbers that the discriminator would attach to real images. Now let's look at the second term. Again, we look at it from the point of view of the discriminator. We are sampling, now we have an expectation, but now we're sampling a random vector z according to the whatever probability these z values are sampled from. So typically Gaussian or uniform, whatever. And then what we have here is the discriminator output for a fake image that is generated by the generator and taking as input this z value. So in the best case, the discriminator can hope to output a 0 here. But since this is kind of reversed with the logarithm, so we need to compute 1 minus 0, so that in this case, the best case output for the discriminator would be 1 overall, since this thing is 0, the whole thing is 1, and then the logarithm would create the logarithm of 1 is 0. So in the best case for the discriminator, this whole thing would evaluate to 0. Now, if this value is higher than 0, let's say 0.5 or something, then the final output would be negative. Now, the discriminator wants to maximize this, and the generator wants to minimize this. However, there is one thing when we look at it from point of view of the generator. The first thing we notice is that here this first part doesn't depend on the generator at all. So when the generator tries to minimize this whole thing, there's nothing the generator can do about this first part. Looking at the second part from point of view of the generator would like the discriminator, ideally here, to output a 1 for the fake image. Then 1 minus 1 would be 0, so the logarithm of 0 would be minus infinity, so that's like the absolute worst case for the discriminator and best case for the generator, because the generator tries to drive this whole equation to minus infinity. Also, just to highlight the point that we discussed before, in this equation, the discriminator has the inner max. So this is an advantage for the discriminator. That means that for every possible choice of a generator G, the discriminator would get to decide how it would like to behave, and then out of all these possible maxima for the discriminator, the generator can then try to minimize. So in this particular equation, the discriminator is at an advantage. Putting a temporal interpretation to this, you could say that the generator is forced to move first, and then the discriminator can decide how it wants